Atoms construct every physical object in the universe, yet for nearly all of human history, they remained completely invisible. Early scientists sought to penetrate the microscopic world using optical lenses, unlocking biological realms built from cells and microorganisms. For centuries, researchers assumed observation had no absolute limit. They believed that by continuously polishing better glass and stacking more sophisticated lenses together, they would eventually resolve the smallest structures in existence. They were mistaken. The barrier preventing them from seeing atomic architecture was not a failure of glass engineering, but a physical boundary built directly into nature itself. To understand this boundary, compare visible light to an atom. Light travels as a wave, measuring roughly 400 to 700 nanometers across. This introduces the diffraction limit. An optical microscope cannot distinguish structures smaller than half the illuminating wavelength. Because an individual atom measures about 0.1 nanometers, it is thousands of times too small to disrupt that passing wave. The light washes right over it, leaving no visual trace. By the early 20th century, physicists had successfully mapped atomic behavior and formulated quantum mechanics using pure mathematics. Yet, despite knowing exactly how atoms functioned, they could not verify their models with direct visual observation. The solution arrived through the work of Louis de Broglie, who discovered that matter, specifically the electron, also behaves as a continuous wave. This visualization maps a central principle of quantum mechanics. As you accelerate an electron and increase its momentum, its physical wavelength shrinks dramatically. Compared to the sweeping, massive waves of visible light, a highly energized electron compresses into a wave thousands of times smaller. Humanity never actually broke the diffraction barrier. We simply circumvented it by swapping light for a much sharper quantum tool. But replacing light with electrons introduced immense structural problems. Electrons scatter rapidly when they collide with standard air molecules, immediately destroying any potential image. To solve this, engineers had to master extreme vacuum technology, building observation chambers entirely emptied of atmospheric gases. Furthermore, an electron stream cannot pass through a traditional glass lens. Researchers invented electromagnetic lensing, relying on dense, perfectly calibrated magnetic fields to bend and focus the electron trajectories. Because these ultra-short wavelengths are highly sensitive to interference, early laboratories required massive vibration isolation platforms and heavily stabilized electrical currents to prevent image distortion. Building the machine required merging two entirely distinct engineering disciplines: the creation of absolute emptiness and the precise manipulation of quantum particles. When the first functional electron microscopes came online, structures that had eluded centuries of optical investigation, like viruses and the precise crystalline defects hiding inside metals, finally emerged into view. Today, transmission electron microscopy drives modern semiconductor manufacturing. It allows engineers to inspect the nanometer-scale architecture inside modern AI processors, catching microscopic flaws before fabrication. What began as a highly specialized physics experiment expanded into the foundational diagnostic tool for both advanced material science and structural biology. Static observation is no longer the limit. Researchers are now capturing matter evolving and chemical reactions in real time. The modern objective is to produce a living, dynamic record of how physical reality continuously constructs and reconstructs itself. To look directly at the foundations of the universe, civilization had to abandon its oldest method of observation. We turned off the light and let quantum waves reveal what was hiding in the dark.